Okay, in lesson 2.2, we're going to look at linear and angular speed again. We're going to look at some applications and sort of how we convert between linear and angular speed in real problems. So first, I want you to recall that we said that linear speed was defined as the distance covered over some time t. And so the textbook is using v, probably for velocity, is equal to s over t, where s represents the distance. I think it makes more sense as v equals d over t. Speed is distance over time. Or maybe v is change in x over change in t. All these are fine. But the point is, if we go some distance in some time in a straight line, that's linear speed. We also talked about angular speed. So angular speed, textbooks use the formula omega is equal to theta over time, where theta is the change in the angle. So you might, I don't know, I kind of like W equals, or omega equals change in theta over change in time. But the idea is if we have some rotation and we sweep out some angle theta, we're just tracking how theta changes over time. And then recall that we said that rotating objects also have linear speed at each point. Okay, they have linear speed, or I should say points on rotating objects have linear speed. So for example, if I have a point here and I'm rotating around in space, that point actually does have some linear speed. And the way we think about that is as the circumference of the circle that is being rotated is kind of like our linear distance. So I like to imagine we unwrap our circumference, and that circumference gets turned into linear distance. So the amount of distance that we're covering in a linear sense is like how many times or how much or how are we going around this circumference. So for example, if we have a radius of 3, and let's say we were doing 1 revolution per 1 second, let's say this thing goes around once per second, we could turn this into a linear speed by multiplying by the circumference, 2 times pi times r, because the circumference corresponds to 1 revolution, which would be equal to 2 times pi times r per second. And that would be our linear speed. Essentially, we cancel the revolutions, we get 2 pi r, or we get the circumference, right, is that 2 pi r per unit time. So that's kind of how we end up with linear distance from a rotational distance. And I think that's all we need to think about now. But we also said that as a consequence of that, like say I had a radius of 1 here, that would mean that the linear speed of a smaller circle with the same angular speed is going to be lower than of a bigger circle. So let's look at some problems of how we would interact with this. So let's suppose that a wheel with radius, let's say 3 centimeters, rolls down the road at a rate of 3 revolutions per second. Okay. How far does the wheel travel in 10 seconds? First of all, we're trying to calculate the linear distance. How far does it travel? We want to get a linear distance. And what we are given is a radius, and we are also given an angular speed, 3 revolutions per second. So let's imagine this wheel sits here, and it's rolling down the road, and it makes one full turn. So here's a point on the wheel to sort of just mark it. Here's another point, and we're turning, and we make it one full turn. How far did we go? And the answer is going to be one circumference length, right? As the wheel turns all the way around, we cover one circumference of the wheel. And so that's one circumference per one revolution. And we have to do this, we said in 1 second per 1 second. We do this 1, 2, 3 times. Oop, and we're off the page. Oh well. So I bet that would bother some people. Let's scoot that down. And there we go. Okay, so here we go. The wheel gets back to start. We're still turning, still theoretically turning. But here we go. We go another circumference, and we go another circumference. And we go one more rev, and we go one more rev. All right, so now we can start to convert things, because we can calculate how many centimeters their circumference is, right? C is just 2 pi r, which in our case, the radius is 3, so the circumference is going to be 6 pi. Okay, so that means we go 6 pi centimeters every time we do a revolution. And then from that, we should be able to piece everything together. If we look at it from a dimensional analysis perspective, we say we go 3 revolutions in 1 second. We multiply that by going 6 pi centimeters, their circumference. Let's highlight that. 6 pi centimeters is the circumference per each revolution that we do, 1 rev. So that means that we're going 18 pi centimeters in that 1 second, because this whole thing here is 1 second. 3 revs in that 1 second. Dimensionally, the revs cancel. We're left with the units of centimeters per second. So now we've converted to this is a linear speed. This was an angular speed. And this is basically the circumference per rev, like 1 circumference per 1 rev. So that's sort of our conversion factor. Okay, so if we go 18 pi centimeters in 1 second, well, how far do we go in 10 seconds? Very easy. We just multiply by 10 seconds, and we're going to get 180 pi centimeters in 10 seconds. Yeah, so that is how far this wheel would roll down the road. So I hope this visual really helps you out. That's the idea behind what we're doing. The math, we end up just sort of doing this dimensional analysis, but I think it's more important to be focusing on like imagining what's actually happening in the scenario, rather than just going through the motions of unit conversion. All right, let's look at 2 more problems. So let's say that I have a circular disc. I never know whether to spell it with a K or a C. Let's go C this time. With diameter 10 centimeters. Let's draw this disc. So here's a circular disc, and the diameter is 10 centimeters. But the whole point of that is probably to get the radius. So we're going to draw a radius of 5 centimeters. And let's say it is rotating. What happened? Is rotating at a rate of 20 radians per second. Okay. So I'm going to ask 2 questions. One is, what is the linear speed of a point on the edge of the disk? So the first thing we want to do is start with our given information, which is that the disk is rotating at a rate of 20 radians per second. So we are rotating at 20 radians every 1 second. And that represents the angular speed. Our goal is to get to the linear speed. So we want to know if we're going around this circle, 1 radian, 2 radian, 3 radian, 20 of these radians in 1 second, we want to know, well, what does that actually mean? So first of all, if we convert the circumference of the circle into sort of a linear distance, we could say that the circumference is equal to 2 pi times 5, or the circumference is 10 pi centimeters. So every time we go around this circle once, we've got a linear distance of 10 pi centimeters. And every time we go around the circle once, 1 full turn in radians is 2 pi radians. So we can use that fact and we can say, well, we're going to go 10 pi centimeters, which is the circumference, every 2 pi radians. Okay? And so if we're going at 20 radians per 1 second and 10 pi centimeters every 2 pi radians we do, that's going to spit out our linear speed. So units cancel, pi's cancel. 20 times 10 is 200, divided by 2 is 100. So you end up with 100 centimeters per 1 second. Okay. All right, so that ends up being the linear speed of a point on the edge of the disk. Then let's ask a second question here. And let's say, what is the linear speed? What is the linear speed of a point that is 3 centimeters from the center of the disk? And so for this question, we can imagine the point anywhere we like. It could be 3 centimeters right here, it could be right here, right here, because the set of all possible points that are 3 centimeters from the center forms a circle, and that circle is exactly the path that that point is going to be rotating in. So we're going to use the same idea. We're going to start with the angular speed, 20 radians every 1 second. That's how many radians of rotation we are doing per unit time. But this time, this point, while rotating through those 20 radians, is covering its circumference every 2 times pi times 3 centimeters, or its circumference is equal to 6 pi centimeters. So every time we do one full rotation, we go a linear distance, if we stretch out that distance into a straight line, of 6 pi centimeters. And that occurs every 2 pi radians. So we'll use our conversion and we'll say we go 6 pi centimeters per every 2 pi radians, and then we'll be in linear speeds. The radians cancels, pi's cancel, and we end up with 60 centimeters per 1 second, and that is our linear speed. So this is how to calculate the linear speed, knowing the angular speed, and sort of just working through the units and working through the logic of the situation. And so we're going to put this all together in one more way, with sort of a physics problem, in which we deal with, I like to think of them as being pulley systems. Basically, we imagine we have one wheel or gear or whatever you want to call it. And let's say that this one has a radius of 2, and we'll be unitless for now. And let's say we have another larger wheel. Let's say that this has a radius of 5. And let's say these two wheels are connected by some sort of belt. So around the wheels is some sort of belt, so that as one of these wheels rotates, let's say the larger wheel rotates, the belt that is touching the wheel will also be rotating. And so the large wheel rotates, moving the belt moves along, and it causes the smaller wheel to also rotate. And the belt is all rotating this whole way. So the belt's rotating, the wheels are rotating, and we have this sort of pulley system. And you could imagine sort of like the gears on a bicycle, or there's all kinds of applications of this in engineering and physics. And so the question is, how does this relate to linear and angular speed? And here's the deal. The belt can only go one speed, okay? That belt can only go the speed of the belt. There's only one belt, so the belt can go one speed, okay? The belt is moving at a linear speed. Okay, we consider the linear speed of the belt, and we want to know how much linear distance is the belt moving per unit of time. If the belt is moving at a linear speed, and the wheels are both attached at the belt, and the belt can only go one speed, that means both wheels must have the same linear speed. Very important idea. If these wheels are attached in some way, like by this belt or some pulley system, they must have the same linear speed because that belt's moving at a speed, and so it's turning the wheels, and the wheels are turning at that speed, one linear speed. But we have something to note, but they are different sizes, the different size wheels. So what happens is that they must have different angular speeds. So must have different angular speeds or be rotating at different rates. Okay, so let's go through and make up some numbers here. Let's say, and let me label this as wheel A and wheel B. Say wheel A is rotating, and let's just do revolutions at, let's say 3 revolutions per second, okay? First, let's say what is the linear speed of the belt. Okay, well, the linear speed of the belt is going to be the same as the linear speed of A. So let's calculate the linear speed of A. A is going at 3 revolutions per second, so we can say 3 revolutions every 1 second, times the circumference is the linear distance of 1 revolution, so that's 2 times 5 times pi, which is 10 pi. So it goes 10 pi, let's throw down centimeters, keep track of a unit. Centimeters for every 1 revolution. It goes 1 circumference in 1 revolution. And so we end up with 30 pi centimeters in 1 second. And that is the linear speed, and it is the linear speed of A. It ends up being the linear speed of the belt because the belt is attached to A. And it ends up being the linear speed of B because the belt is attached to B. So it's the linear speed of A, the belt, and B. Okay, so if we know that that's the linear speed of everything, let's say I wanted to ask you, what is the angular speed of wheel B? Okay, and we're going to use what we just calculated. We know the linear speed of wheel B is that we're going through 30 pi centimeters of rotation every 1 second. Now we need to turn this into some angle measure or number of revolutions per second. And so if we think about B, every time we do 1 full revolution, we do 1 circumference of linear distance. And the circumference of B is given by 2 times pi times 2, which is 4 pi. And so every time we do 1 revolution, we go 4 pi centimeters, okay? And we know we're doing 30 pi centimeters per 1 second. And then every time we're doing 1 revolution, that's accounting for 4 pi centimeters. Putting this all together, we'll end up with 30 over 4. And in this case, I'm going to use a decimal. We're going to get 7.5 revolutions every 1 second. So in terms of angular speed, if we choose to express it in revolutions, we get 7.5 revolutions per 1 second. And that's a good enough way to express it. If you wanted to convert that into radians per second, you could say times 2 pi radians per 1 rev. So we could also have an angular speed where it would be 15 pi radians every 1 second. So that's an alternative way of expressing the angular speed. But the idea is that the linear speeds of the belt of A and of B are all the same. And because B is bigger than A, it must be, or sorry, that A is bigger than B, that means that their angular speeds must be different. For all of this to be the same, B must actually have a greater angular speed than A. So A, if we recall, to compare, was rotating at 3 revolutions per second. So A is going around 3 times in a second. B, we said, must be going around 7.5 times in a second to have the same linear speed, because A sweeps out a larger area every time it turns around. So to have that linear speed of 30 pi centimeters per second, A only needs to go around 3 times, whereas for B to have that same linear speed, it actually needs to go around 7.5 times to cover that same distance. Okay, so definitely practice with those, think about it. Definitely takes a little bit of getting used to, but these are the main ideas, and these are the types of questions that you will encounter as far as pre-calculus goes. There's lots of applications in physics and engineering between linear and angular speed. And it's great practice working with rotation, and it's great practice working with radians and unit conversion. So there's a lot of value to it. Hopefully you enjoyed this video, and thanks for watching.